Bismillahirrahmanirrahim. For 3D elasticity, we start with the same equations, obviously, the same general equations for FEM that we started from when we dealt with 1D and 2D problems. Just a reminder, this is the basic equation for steady state, and where K is you're very familiar with these expressions by now. This integral, this is for one element, and you have to make this expression for every element and then assemble them for the whole body from element 1 to E. And this assembly, this was done by the connectivity table. You recall, I'm sure you recall this. We have done it many times. And this part is for each element. What about the F? This U, obviously we want to find the U in these situations. And this F, this is again a combination. Thermal, the force vector because of temperature changes, body force vector, distributed force or pressure force vector, and then you take this is again for each element, and then you take a summation from element 1 to element E being the total number of elements, and right at the end you add any concentrated forces that are being applied. There's no summation involved there because they already are applied to nodes. Now each of these again, and this is done by a connectivity table, this one. So you make these vectors for each element and then connect them using the connectivity table, that is your assembly, and then at the right at the end you apply the concentrated loads, if any. Now what about the expressions for these individual force vectors? The first one is again, this is very familiar. We have done it for 1D and 2D, so there's nothing new about these here. Their application will be slightly different in 3D, but that's just the application. So this is your again a volume integral. So this volume integral, this is for one element. This is for one element. This will be for one element, and then you assemble them all together for all the elements, and that is done by connectivity table. So there are two types of integrations involved here. You are familiar with these things. These were the general equations. Body force vector, we have this. These are the body forces. These are in Newton per cubic millimeter, applied to the whole of the body. And then you have this time this is a surface integral, again shape function, you know this matrix, and these are the pressure forces. This is the surface integral, and these forces are in Newton per square millimeter. So we are going to apply these same equations to our topic today, which is 3D elasticity. The process will be very familiar. I may skip some steps because it's a longish derivation for some things, but it's no more difficult than it may be lengthy, but the concepts are the same for 1D or the 2D problems. So I'll just list down all the expressions, and you can verify them for yourself. And some of the things we have already done here. Some of these things we have already covered, and you will notice that in many cases we'll be just extending our treatment of 2D problems to in a way you can look at it like extending our treatment for 2D problems to 3D problems, but obviously we are basically doing it from the start using these expressions and then reaching our conclusions, although we may skip some steps. So we always start with the n matrix because we have n matrix here, and then we go on to B matrix and all that sort of thing. So n matrix, basically you recall it links or it joins the nodal displacements to the general expression for displacement. Now here this is general displacement vector and this is the nodal displacement vector, and there's nothing new about these. We have done these at least 2 times before, but in this case for 3D problems, now this u will take, if we write all the components, it will take this form. Obviously for 2D it was just u and v, for 1D it was just u, it was just a number, but here, and we have seen this expression, you have seen in one of your earlier lectures. You're familiar with this expression, how which matrix links these general displacement vector to the nodal displacements. And the displacement vector in this case, the nodal displacement vector, you must recall here that we are talking about simplex element. We've been dealing with simplex elements all along. So for 3D also we are discussing the simplex element first. If this is the coordinate system, now we have the z-axis as well. So for example, this is the I node. Let's say this is the J, this is K, and this is L node, 4 nodes. Now for each node, there is a Uj, a Vj, and a Wj. And the same goes for example, Vi, Ui, Vi, Wi. So each node has 3 degrees of freedom, and you have 4 nodes. So you have 12 degrees of freedom. Now 12 degrees of freedom mean you must have 12 elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that makes sense. And here you have this Ui, Vi, Wi, Uj, Vj, Wj, Uk, Vk, Wk, and Ul. Now we have an L node also. Vk, Ul, Vl, Wl. This is your, and this is familiar for you. We have done this. This is not the first time that we are doing this expression. Now, this is the n matrix, and these are the shape functions. Now, what is the expression for the shape functions? Again, we have a general expression. We may not have derived it till the end, but we have derived the same expression for 2D problems, and that was very similar to this one. Slightly different, but you can follow those steps and reach this situation. It's lengthy but not that difficult. Now this is for beta. Now beta, the index beta, it is I, it can take the form I, J, K, and L. So you can have all these values, just replace beta with I, J, K, and L, and you get these expressions. So this is so far as the n matrix is concerned. Now if we have taken care of this, then the next thing to take care of is this B matrix. Now B matrix, what is B matrix? It is nothing but a matrix that links the strain vector with the nodal displacements. Now here again the concept is very similar to 2D problems, although here we have more strain components, obviously it being a 3D case. So let's recall what are the components of strain. The components of this should be 6 in number now. A very basic continuum mechanics or solid mechanics. So you have this third linear component also, which wasn't there obviously in 2D problems. And as far these are the normal strains, and as far as the shear strains are concerned, you have again very simple expressions, nothing difficult about them. These are the shear components. So now we must see what this expression looks like, and it's not very difficult to see because it is just, if you have this, we know that B matrix is obtained by some sort of differentiation of these matrices, this n matrix, because this situation, because n matrix gives you the values here. So it has a constant, it has an x component, y component, z component. So when you differentiate with this with respect to this respective x, y, z, or in some case mixed, then you get the B matrix. So there's nothing difficult about it. Let's see what shape it takes. So let me write it in a complete form here. Now here we have some the coefficients a, b, c, d. You can just look them up, their details in your textbook, and they are very similar to, obviously they are larger expressions, but very similar to the 2D case. So you have expressions for these in terms of the the geometric coordinates of the body of the element. So this takes the if you have put in those values and differentiate appropriately, for example for epsilon x you differentiate this u with respect to x, and because it's u, then you're talking about with respect to x, so these will be irrelevant and only this will remain, and so on. So if you do this simple differentiation, you get this expression, very easily verifiable expression, albeit a little large expression. Very systematic. You can see the pattern here. Finally, this is your expression for the appropriate you get when you appropriately differentiate this. You use v's and w's with respect to the respective coordinates, and this is what you get. Obviously on the right hand side you have the same thing. This vector doesn't change. You have 12 degrees of freedom, so ui, vi, wi, uj, vj, wj, uk, vk, wk, ul, vl, wl. These 12 degrees of freedom for each element, they don't change. Now this matrix is the B matrix, and its size is 6 because 6 components into 12 because there are 12. So it's 6 into 12. Now once we have dealt with this, obviously we can deal with this now and this, and the next thing that we need to deal with is this D matrix for 3D cases. Again, it's well known when we talk about the D matrix. Here its application is the stress and the strain vectors are joined together with like just like n linked the general expression of u with the nodal displacement, b linked the strain vector with the nodal displacement vector. Here d links the stress vector with the strain vector. Now here again you have 6 stress components, so you have again six strain components, so you have six stress components as well, and actually they are 9, but 6 are unique ones, the other 3 are just, if you recall the complementary property of shear, they are just the same. We have tau xy, tau yz, tau zx. We are talking about tau xy and tau yx, these are the same. Similarly here, so we just 6 should suffice. And the expression for 3D, this is again well known for in solid mechanics, very well known expression. Most of you have already are familiar with this. Those who aren't should get themselves familiar with this very important expression for 3D cases. You cannot do any transformation from strain to stress without knowing this expression. So this is your expression for, and those who have in mind plane stress and plane strain case, just for memorization sake, they should note that the shape it takes is very similar to the plane strain case. Not that the dimensions are different, obviously you have more components, but the shape, these quantities, they are exactly the same. These quantities are also the same, although we have to add some extra dimensions to it, obviously. Now this takes us to the next quantity of importance, and that is epsilon naught. Now, epsilon naught, if you know the epsilon naught, then we can then move forward. And this epsilon naught is for 3D cases. It's simply, I was talking about initial strain vector or thermal strain vector. Initial or thermal strain vector, and we are talking about cases where you have change of temperature. Obviously, if there's no change of temperature, there's no such thing as, you don't need to think about that. So let me first write it and then I'll explain it. This is for 3D cases. This is the initial strain vector, and what we are talking about here is, if you have this sort of a body, I'm talking about an element here, and this is your coordinate system, and you subject this thing to a temperature change of delta T plus delta T, then it increases in length x direction, y direction, and z direction. So there will be strains, thermal strains, and which are associated with no stress here, because it's just thermal strain, not mechanical strain. So you have this strain in 3 directions, x, y, and z. But as far as the shear components are concerned, they have nothing to do with thermal strain, because shears would imply changes of angle here, which don't take place with the temperature change alone. So what we're talking about here is, just to make it clearer, this is the epsilon x component, this is the y component. I'm obviously talking about the thermal Every one of these is thermal, and these gamma xy, gamma yz, gamma zx, again thermal, thermal. They have nothing to do with the temperature. So you can write this in a simplified form: alpha delta T 1 1 1 0 0 0. So this is your expression for the strain, the initial strain vector. Now we are in a position to, because now we have at our disposal all these quantities. This we know, this we know, this we know, this. So we cover the whole area. Now the next step would be to apply these, to use these to get the expressions one by one. So first of all, we start with the K matrix. Again, we are talking about element. We're talking about element K matrix, and what we talk about here is this expression only, because for each element you'll have to make this, and then this is just assembly. You don't need to do it here. For every problem there will be a connectivity table and you assemble according to that, but here we are talking about this one. For each element you can deal with one element, then you can deal with all elements, and here it's element of volume of an element. So I'm not writing E here, but we're talking about an element here. Now in this case what we're talking about is this B, D, these are all matrices which are basically exclusively they consist of constants. So you can take these out from the integration, and this thing is nothing but the volume of the element. So you can write this expression, and you just apply V here, again volume of the element. So K for 1 is simply this. Now you should verify for yourself what should be the size of this, because we will know the volume of each element. For example, if this sort of an element is there, talking about 4 node simplex element, so this whole volume, this will be this. B, you have expression for B. We just saw the expression for B, and this one, this is B. So B transpose, you can just get the B transpose. D, again we have just seen the, so now this B transpose, if you see the dimensions of it, it is 12 into 6. Now this D is 6 into 6, and this B is again is obviously 6 into 12. So the size of this turns out to be 12 into 12, which makes sense obviously, because at the end you know that for each element there are 12 degrees of freedom. So even if you see this at an elemental level, Ku is equal to F, this has 12, so this must be 12 into 12, and F should also be of 12 into 1. So 12 into 1, 12 into 1, and this is 12 into 12. So makes sense. And for each problem we'll just assemble B for each element, then transpose it, take D, and then use this expression to get K, which will be 12 into 12. Now we come to the force vector, again elemental level, because of temperature change. The expression, again, this is for volume of the element. We're talking about element level here, so I'm not writing E here, but it goes without saying. This was the expression. Again, all these B transpose D, none of these contain any spatial coordinates, so these are just constants. So you end up with this sort of an expression. This is nothing but V, again the same V, this same thing. So in the end you get V B transpose D epsilon naught. You already know what this is. D, again we know, and if we put in the values, it's very easy to see. It will take about 3 minutes or less than 3 minutes, maybe 2 minutes to reach this expression. what happens is, because there is a B transpose here, so there is 1 over 6 V involved. So V cancels out with this V, and if you multiply these expressions, and I can demonstrate here that this one is B transpose. This is 12 into 6. This is again 6 into 6, and this is 6 into 1. You just see this is 6 into 1. So actually when you multiply them, you should get something which is 12 into 1. And sure enough, you get 12 into 1. And this is a very simple expression, similar to the one that we derived for plane stress, plane strain. Obviously, slight differences here, but this is your initial strain vector. And sure enough, 12 into 1. Because if this is 12 into 12, K force vectors must be 12 into 1. Displacement vectors must be 12 into 1 for each element. 12 because 4 nodes, each node with 3 degrees of freedom, this being a 3D system. So this takes care of this and this one. Now we are left with body force and pressure forces. Let's take them up as well. So the expression for body force vector at an elemental level is again a volume integral, this time with shape function and x, y, z, and this is again at a elemental level. This should be E here. I'm talking about, but because E is here, so it's understood. So I don't want to add extra things here, unnecessary things. But you get the point. So if this is the case, then again NT is if you recall your factorial formulas, it should be very easy to see that for using factorial formulas you can, because we have formulas for simplex elements for any quantity including these shape functions. So if you open these shape functions, write them, I'm talking about this in an expanded form like this, take transpose, you can just use the factorial formulas and get your but obviously you'll be using the volume integral formula, and you can see that in your textbook. So if you follow this and in 2 or 3 steps, it's very similar to the ones we did for 2D problems, you should reach this expression. Now here, unlike 2D case where we only had x and y, not z, because it was a 2D problem. In 1D there was just x. Here you have all three. Again 12, and very simple treatment from here to here, so you should verify it for yourself. Now just look at this the dimensionality of this NT. This is 12 into 3, the dimensions 12 into 3. This is 3 into 1, obviously it's visible here, so you should get 12 into 1, and indeed you get 12 into 1, as should you get, and so there's nothing wrong with this. Now let's talk about it for a while. What does this mean? Again, very familiar. If this was the element and we're talking about some xyz force pulling it from this direction. Now what you're doing actually is, this expression gives you that this xyz, this is in Newton per cubic millimeter, this V is in cubic millimeter, so when you multiply them you get the total force in newtons. Now what we are doing is, we get the total force in Newton in the x direction, divide it by 4 and apply it to all the nodes equally. Actually what we're doing, node I, node J, node K, node L. So if this is I, this is J, K, L, so here we apply Vx over 4. This is just 1/4 of the force applied in the x direction. Here 1/4 of the force applied in the y direction. Obviously I'm talking about this coordinate system, and here pz over 4, 1/4 of the force applied in the z direction, and the same goes for, so all we are doing is the total force is being applied on this whole volume, and the force has maximum 3 components. It could have one component like in the case of weight, but it could be in any direction, arbitrary direction, so you may have a maximum of 3 components. So for each component you just multiply with the volume, you get the force in newtons in that direction divided by 4, and then apply equally to all nodes. Same goes for y and z direction. So it is exactly the same thing that we did for in the case of 2D, and the dimensions as well as the size, they just make sense, also the units. So now it takes us to the final pressure force, and this is a surface integral, unlike the body force. This is a surface integral, and what we're talking about here is these are in Newton per square millimeter, these forces. So what we're talking about actually is this: if this IJKL, then maybe on this side only the pressure Px, Py, Pz in an arbitrary direction is being applied on the whole. So obviously the integral must be on this surface, not on the volume like the case with the body force. So we have to take the area integral here. And again, if you use the factorial formula, now this time again for area, it can be shown very easily that the answer you get is Sijl over 3 Px, Py, Pz, Px, Py, Pz, 0, 0, 0. I'll explain these: Px, Py, Pz. Again, as far as dimensionality is concerned, this one is 12 into 3. This is 3 into 1, so you get 12 into 1, as you should. And what does this mean? What it means is simply that whatever the Px, Py, Pz components are, you just multiply them with the area on which they are applied. So the area would be, in this case, IJL, Sijl. And because this is Newton per square millimeter and this area is millimeter square, so you get something in newtons. Now the force you get in newtons in the x direction, you just divide by 3 and apply equally to all these 3 nodes, and you don't apply it to the k node. Obviously it has nothing to do with it, it is an interior node. So what we're talking about here is, if this is your x, y and z component, then here the force you apply, this is j node. Basically you're talking about this point. So the j node, you apply force of Sijl into Px over 3. Similarly, I node, Sijl over Px over 3. L node, Sijl Px over 3. Similarly, y component, z component. But you only do it for I node, J node and L node. You don't do it for the K node. In this case, if obviously the force was being applied here on this area, then you would have used I, K and L, then the 3 zeros would have come here in this part. So you are familiar with this concept for in 2D problems as well. So what we're talking about is this. Similarly, in the y direction you'll again have the same expression for with Py. In the z direction you'll have with Pz, but only for these 3 nodes. Now that brings us to the end of this topic. I'll just mention one point, that even very simple 3D problems, for example 2 or 3 elements, they can be a handful, because just imagine 12 degrees of freedom for each element, and if there are 3 elements, you just imagine how many degrees of freedom it becomes, because when you assemble them together, it becomes a big system. So for hand calculations it is very difficult, but there's nothing difficult about them when you use a computer. So because if you know the concepts, these are the concepts, just like the 2D concepts. In 1D cases you could do all the problems by hand. In 2D cases you could do parts of the problem by hand. Here it is even difficult to do parts of problems, some parts exactly. For example, assembly, it will be very difficult. It will maybe cover this sheet and you'll need some extra space even for 2 or 3 elements. So but that's just manual calculations. In computer, there's nothing difficult. If you understand this, you can just do it. The other thing, again, just a reminder that when we talk about the this expression, when we talk about this expression, we must be very clear about this. This epsilon here, I'm sorry, this I should. Here I just missed epsilon x, obviously epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. Now this is complete expression. Now if you use this expression to get this, which you do at the end of the problem, you must make sure that this is a vector of mechanical strains, not total strains, because recall, when we formulate the problem, we always apply this initial strain vector, that which is a result of temperature changes in it. So the result you get, the displacements you get as a result of FEM, they include total strains, including thermal strains as well as the mechanical strains. So when you are going to apply, and obviously after that, ultimately you get this using your, if you know these, using B you get these, but these again are total strain vectors. This is a total strain vector because it includes the effects of thermal strains. Now if you use this expression as it is here, you'll get an overestimation of stresses. Actually, between this step and this step, if there are temperature changes involved, then you have to remove the effect of thermal strains from this one, and then that will give you the mechanical strain. So this step is very important. Again, I'm just writing because this is one of the major mistakes that are done here in these problems, that when you use this expression, you must use in this form if there are temperature changes. And this expression, this you know, or this is simply this one. So whatever strain vector you get, total strain, you remove this part and you get the mechanical strain. And once you, this is mechanical strain, this total one, and then you can get the stresses. And if there are no temperature changes, obviously this becomes 0, so then there's no issue. So that's the end of this lecture. Thank you.